years to collect and model and interpret intra-individual data, or intensive longitudinal data, it's also called. So I've set up the presentation in different parts. We're going to start with what a process is, then see how we can model this, so a bit of statistics, and then look at some empirical findings of studies where we have both student and teachers reporting on the same event, and then also to look at some links with objective outcome measures, and then to conclude on further steps. So welcome all. So let's first look at processes and see what it is. So we've tried to distinguish between what development is and what a process is. If we start up here with the macro time scale, yeah, here is my pointer. Yeah, macro time scale. This is time scale that can be measured in years and months. And the figure here underneath that text, it shows 2 sample students. And the time here is on this is time in months. And we see that one student overtake the other, and then they cross paths, and then develop in slightly different rates of acceleration over time. If we then really take a look at this, magnify this point here, we can see that we have time in days, and this kind of meso time scale in days and weeks, during which we have kind of see development. These are quite flat lines that we see over time. And then we go to the micro level, and here we then see a lot of fluctuations from one time point to the next here at the micro level. This is really the process level. This can be hours and lessons, and it can also be broken down further. If we look at tasks, then this can be seconds and milliseconds during the progression of a task. There is a lot of interest in this type of research out there, and here are my German colleagues who are using this as a framework for personalized or individualized learning. So in order to understand how we can support students individually, we need to know what the individual processes look like over time. So how can we investigate educational processes? We start with distinguishing between states and processes. So a state is an experience in a situation, and a process is then a sequence of states or a transformation of one state into another. And the important educational research questions to pose are: what do teaching and learning processes look like, and what effect does teaching have on such learning processes? And this comes from Bernard Schmitz, our senior time series modeler in this field. So we need to investigate processes as they occur in real time, rather than asking people retrospectively what they have experienced. Studies like this are called intrapersonal, microlongitudinal, within person, or geographic research. This can be done by so-called experience sampling, ecological momentary assessments, or diary studies. And what all these have in common is that they reduce recall bias and they increase contextual closeness. We know from studies of memory that episodic memory is replaced by self-perceptions within the time span of about 24 hours. So we really edit the experiences that we have experienced quite soon after they have experienced. We try to capture them as soon as possible in time. So we observe individuals in real time, and we can also link this with ambulatory assessments. So these are biophysiological measures that also occur in real time, like eye tracking or gaze. And we can also link this with trace data from computers that all have timestamp data. There's a huge interest in this type of research in all social and medical sciences. And in medical science, this is also used for tracking patients and looking at their various symptoms of diseases and tracing those over time and warning people when the fluctuations are too high or too often. And multimodal data like this is getting really easier to collect with all kinds of technical gadgets that we have. Can implement apps on any electronic device and collect data that way. So let's have a look at time. We need to distinguish between chronological time and social time. Chronological time, this is now a statistical idea. We have time point t here in the middle as a starting point, and then we have t minus 1, t minus 2, t minus 3, and so on. And then we have the subsequent time points there, t plus minus some coefficient. So we assume that these can be equally spaced over time. For example, if we have a diary study, everyone completes a diary in the evening. This would be quite equally spaced time lags between the observations. But if we want to go into educational settings, we can see that there's also a social time element. For example, we have day 1 and we have 4 lessons during the first day, lesson 1, 2, 3, 4. And then we have a lag until the second day. And we can also see some lags between lesson 2 and 3, 6 and 7 there in day 2. So here we don't assume that the time points are equally spaced. And in fact, we can also investigate whether the daytime lags differ from the nighttime lag that we have in between these 2 days. So there's a lot of missing data here, if we say so. There's this downtime. The students are off from school. They play, they relax, they do homework, they watch telly, they have a meal and go to bed and wake up the following day. One can also think of spacing what happens within lessons. So for example, 3 observations per lesson. So this would be beginning, middle, and end of a lesson. And then there can be quite a long lag if these are mathematics lessons. So the following math lesson is the following day or after 2 days time. And that gives quite a long lag in between. So these are possible to adjust for also statistically. And this is just how the real world operates. So if we think of time points as discrete time points that happen one after another, we could think of these as rank ordered time points. And here we have the chronological time in kind of equally spaced units, and then we have social time. Does that make sense? Yeah. So there are a lot of concepts now that we use in the field for conceptualizing what happens over time. So we can think of stability. This is something that is carried over, or inertia, from one time point to the next. And the statistical unit to look at is the autoregressive coefficient. So this is the association between what is happening in time point t and t minus 1, so in the previous time point. We can also think of variability. So these are the ups and downs, so the oscillations that we can capture within a person. So this would be, for example, the standard deviation of the observations over time. So how much variation there is within a person. Then there are 2 more measures that are quite similar, but also distinct from them. The next one is instability. So this is the magnitude of the fluctuation. So not only how variable they are, but from one time point to the next, how large the fluctuations are. And this can be captured by something called mean sequential square differences, or the square root of it. And then we have volatility. This is the unpredictability of change. We can estimate whether the residuals in a model are actually different from one person to another. This is something that hasn't been done a lot yet, because we're predicting unpredictability, and we don't really know what it is that causes the unpredictability, everything that isn't measured in a particular study. But statistically, we can get that. And this is all different from the mean trend. So this is the change in the observations over time. They can increase or decrease over time, or have any other shape. And we can look at beta coefficients there. And then we have stationarity, a term that is used in time series modeling. This means that there is no mean level trend over time. I mean, individuals just oscillate around their own mean or their own average over time, and also that the associations over time are stable. So these are all things that people look at. And let's look at some stationary time series models with different autoregressive parameters. So the autoregressive parameter is the number here, 0.8. So this is a strong association between t and t minus 1. This is a lack of association between t and t minus 1 in the middle, and then a negative coefficient between t and t minus 1 furthest down. In the top graph, we see that there is so-called inertia. We see that the trend over time takes quite a long time to get back to the average of the individual. So this is called inertia. If we compare that with the mid graph, we see that there are fluctuations and individuals hit their average quite often during that trajectory. And in the negative association, we've seen that there are large fluctuations, like here in the middle, really. And this is really that the previous time point predicts positive event and then a negative event, and these then fluctuate back and forth. So positive, neutral, and negative autoregressive coefficients are some things that we'll look at. Time series in practice. So this is a diary study by a patient who suffered from depression, and he kept his own diary over 5 years, and this is the last year. So these are all the 365 days where he has recorded his mood and with his own scale. So this is by Groot, 2010. It's a very interesting paper. It's kind of self-monitoring of his own mood, and it's publicly available. So he published it in his own name. And it's a very interesting paper. So these are days in years. And here we have a very different time series. These are trials in an executive functioning session that lasts for some minutes. And we see that accuracies and response times then are indicated in green and red here. These are the accuracies and the response times in green. 12 incongruent tasks are indicated in gold in this, and I'll show you more from this study a bit later. So these are quite different time scales for these time series that we have. We can also have multiple variables that we observe over time. So these are 3 variables for 9 sample cases. We have competence belief in blue, and effort in black, and task difficulty in green. And we see how these fluctuate over time. These are primary school students in England. And we also see that about a quarter of the variance is between students, and the rest of the variance is within students. That means there are a lot of fluctuations over time that we try to predict. Here's another set of 4 example cases of positive and negative emotions. And we see that they all form quite different patterns over time. So individuals really are different in their trends over time, the stability over time, and which direction, how far apart positive and negative emotions are from each other. So a lot of between individual differences in what these internal patterns look like. So we try to model all these statistically. How do we do that? We start with 2 really basic models. The first is an autoregressive model in which we look at whether A is stable over time. So A at the previous time point predicts A at the concurrent time point. And then we include the next model. We include a covariate that is time varying also at the time point T, and of course all the other time points as well. So stability over time and a covariate effects over time. Then we can think of how experiences affect each other over time. This is also called a reciprocal effect model, where we have A, stability of A, and stability of B, and then the cross flags here. How does previous B predict concurrent A, and how does previous A predict concurrent B? And this is a model that I'll show you later, where we, instead of having these as 2 variables within a person, we have this as a student report, and this is a teacher report of the same event. So that will be interesting to see. So stay tuned for that. And this could, of course, then be a self-report measure or an objective measure. Then we expand these models and we look at so-called individual differences in process parameters. This is indicated with these black dots here. So those are random terms. And what we can then see, for example, the random term for A is that there are individual differences in the average of this variable between one individual and the other. If we plot these 12 or so sample individuals here, we see that the average among all these persons is 4, indicated here. And then we see that the individual means are different. And also the within person variability is different across all these people. If we then look at the individual differences in stability over time, so this dot here indicated in red, and the average stability is 0.1, and there are individual differences. We see that these also can vary across individuals. So some individuals have negative autocorrelation, so that means a pattern where negative and positive oscillate a little bit, and these are more positive stability, stronger stabilities. So individual differences there as well. And then we can also look at effects of covariates. We allow the covariate effects to differ across the individuals. And here we then can see that each line now represents one person, and we see that those are different regression lines for each person. So covariates have different effects on different individuals. And then we turn to a monster model, and I think this is currently as close as to the nirvana of statisticians as we can get in the world of modeling. And this is based on Hamak et al. And we can see that this reciprocal effect model here can have 6 random terms, and those can all be modeled as individual differences. So here's the A-B parameter. So A regressed on B, and we allow individual differences in that parameter. For example, we have different slopes again for each person. And then we include covariates and predictors and moderators. So moderators typically at the between level is what. So if we find individual differences, can we then predict those? And then we can look at covariate effects at the within level to see if we can predict some of the typically quite large variance between time points. And this can be expanded to a 3-level model where we have time points in students, in teachers, or in classrooms. And it can also be specified as a cross-classified model that we have time points, but they're nested in both students and in teachers. And we'll see an example of that coming up. So there has been quite a surge in studies like these in education and educational psychology, but also in other disciplines. And there's critique mounting against these studies. So first of all, the self-report bias here. So if you rely only on self-reports, then reviewers and journals are beginning to turn these down and say, well, it's good to know what individuals think and feel, but we also want to see if we can link this, for example, with objective measures, for example, task performance or biophysiological measures. And we can have multiple reporters instead of single reporter studies. And then correlational designs can be expanded to experimental designs. I haven't tried this myself, but there are experiments coming up. They're called nudge designs, where instead of having a control and experimental group, you have control situations and experimental situation where you give nudges to people, so some prompts to act on or to self-evaluate, and how these then can individually affect the kind of trends over time. So designs like this are beginning to show up. Are you all right with that? Okay. So let's take a look at some multiple reporter studies. Let's start with a study of English children called the Learning Every Lesson study, carried out here in Southeast England for quite a while ago. The second project is by Pei-Xin Li, my former doctoral student. And also the third study by Karin Street, also my former doctoral student. So in the first study up here, we're going to look at combinations of student self-reports every lesson during 1 week's time, linked with the students' teachers' reports of students' task focus and involvement with each student and academic performance of each student. But this is not in each situation. These are person level ratings of the teachers. So teachers rate children once during the time span of the study. So these are more like trait measures. To expand that, we then see teacher reports in the study in Taiwan. We also have teachers' reports of their own emotions in the lessons. So we have both students and teachers' emotions from the same lesson. And then we have also for target students' engagements that are rated by the teacher for target students in each lesson. This took the longest time to report. And then we have Karin Street has observed quality of student-teacher interactions, so a more objective rating of what the quality of education is. So here's the Learning Every Lesson study. The design is that we have up to 5 days and then up to 5 lessons each day. So we had on average 15.4 lessons per participant. And the response time was about 1 minute and 49 seconds. This was because of the text element. The rest of the items were fast to administer. And these are among year 5 and 6 students in England. So they completed questionnaires, and the teacher reports are then reports on students' performance, task focus, and involvement, but once per child. So this is what the questionnaire looked like, and the ancient device that we used at the time. This was 2007, 2008. So we need to upload the questionnaire into the device and then download the data by plugging it in. Now, today, everything is done automatically through Qualtrics or Bluetooth or some other device, and we get the data in an Excel spreadsheet. Here we extracted it and cleaned it and merged it together, so individually for each participant. So it took a bit longer. And then that's what subject are you doing? What was the last learning task? And so on. Here are situation-specific difficulties and competence beliefs. So how the learning task was easy to difficult, how well were you doing, and how much did you understand? These two were combined into competence belief. And then we have the motivation questionnaire. So autonomous and controlled motivation, also called intrinsic and extrinsic motivation. So we looked at the study on intra-individual variability of students' learning experiences. So we aggregated these and linked these with teacher-reported task focus. We modeled this with a structural equation model. Oh dear. So we modeled the observations in the situations here in the middle, and then treated this as a state latent construct and the trait latent construct, and we modeled the variability using the mean squared sequential differences aggregated from the data. So we have 3 latent constructs in this model for each variable. So what the findings look like, we have state difficulties, trait difficulty, state competence, trait competence, state intrinsic motivation, and trait intrinsic motivation, and then the variability of each of those. And we find that higher trait difficulty was linked to more instability in difficulty, and the other way around, higher trait competence was linked with less instability. So variability is associated with the average level of each student. And then to look at convergent validity, we included task focus here in the model. And task-focused students were less variable from one time point to the next. So they stayed on task. We see that the ups and downs are smaller than those for less task-focused students.
Yeah.
Yeah.
I'm struggling with what's the difference between higher trait difficulty and higher trait competence. I mean, I can see higher trait competence, but I would have thought difficulty was a task, a state, not a a trait.
Yeah, so
I'm
yeah, so
stuck with past ideas.
so state difficulties, these are the situational ones.
Yeah,
So this is modeled as a state.
yeah,
And then you take the average difficulty that the student reports across the week. This is the trait difficulty. So we take all the difficulties experienced across the week, and this is the individual's average.
yeah, I can see the statistics,
Yeah.
but I'm struggling with the concept. Because I mean, I'm sure I'm just using past ideas here, but I would have thought difficulty is something of the task and not of the student, and competence is something of the student, not the task.
It's a good point. So let's see how we actually asked the question there. If it's about so the learning task I was doing was easy, quite easy, either hard or easy, hard. So it's about the task, not how difficult it is for me. And this is a distinction between primary and secondary appraisal as well. So you're right, this would be the average perceived difficulty of the tasks over the week.
Okay, so that would sort of maybe vary between lessons.
It does vary between lessons. That's captured at the within level.
Okay.
Yeah.
Okay, thank you.
And this is how much variable they are from one lesson to another.
Yeah.
The oscillations of it.
No,
Yeah. No, that distinction. Yeah.
The lessons are always different subjects.
They're in different school subjects. Yeah. Yeah.
Yeah.
Yeah. And that's the progression in primary school there.
It might be geography, history, math.
Yeah. So they have different subjects one after the other, and this can explain part of the variability.
Okay.
Yeah. So what did we learn here? All students have their ups and downs, and there are individual differences in this instability captured by the mean sequential square differences. Teachers rated engagement or task focus, predicted trait levels, and less instability in those models. So what do we learn about the design and modeling? So teacher reports of students in general, tapping into teachers' accumulated knowledge of students rather than situational experiences of the student. So this is knowledge teachers have that they build up during the, say, first month or two during meeting their new student group. And then this can stay quite stable, this perception of what students are like over time. So these are not situational reports. If we then model the same data and we have a slightly more complex model, we have effort, competence, autonomous and controlled motivation. We will look at these variables. I won't show these complex models, but we'll look at the teacher reports. So the teacher's involvement with each student. For example, spend one-to-one time with her. Each student's task focus, the teacher rated student's task focus, and academic performance of the English curriculum levels. And if we have this correlation matrix where we have effort, competence, autonomous motivation and controlled motivation, performance, task focus, and involvement, we look at some interesting correlations there. So teachers report that they're more involved with students who on average report less effort during the week, those who feel less competent during the week. So it's in teachers target students to get involved with, and this seems like quite reasonable and adaptable way of working with children. We see also that teachers are more involved with students who are lower performers and those who are less task focused. So these are the teacher perceptions, and these are students' own perceptions here. So here, when we link teacher reports, we need to do this at the between level for students. We get aggregates of what students do over the week, so we don't predict what's happening in the situations in this model with the teacher report. So that's what we want to do next. So the next step in the modeling is to include both teacher and student situation-specific data into the same study. And that's what we then did in Taiwan, Beijing Li's study, where we included both students and teachers' emotions in this study, and teachers' perceptions of what's going on in the classroom. So the design is very similar to the previous design. Each lesson, we have students self-reports. Students also report on the teachers, their perception of the teacher's emotions. And then we have a teacher's report of his or her emotions. And then we have target students, teacher reports of target students' engagement over from one lesson to another. And then some additional questionnaires at the individual level. So when we look at the way teachers see what's happening in classrooms at the situation level, so this is the lowest level in the model, we see that the students' disruptive behavior and students' engagement, these are teacher perceptions of disruptive behavior and students' engagement, and those then predicted more or less a specific student engagement, predicted higher positive emotions and lower negative emotions of the teacher, since the teacher's self-report. Those all seem logical and nice, and more student disruptiveness, higher negative emotions. And these are lesson specific. These make sense. Then we have the novel design, where we have teacher reports of 4 target students. And these were selected so that teachers nominated 6 students. And out of these, we then asked the teacher to rate 4. So 2 students who they paid relatively more attention to in class, so higher level of involvement, and 2 who they paid relatively less attention in class. So differentiated between these 2 types of students. And teachers were very good at selecting students and agreeing with this design, that some students get more involvement than others. And teachers had both closer and more conflictual relationships with the students in the high involvement group. So the way they selected these students, there can be the reason for involvement, that they get along well with students or that they don't get along well with students. So we have 20 teachers reported on 80 different students and around 1,000 or so situations. So here is the design of this sub-study. And I haven't seen anyone collect this type of data up to now. So at least to the best of our knowledge, it's a novel design. We then modeled teacher involvement here at the within level. Teacher involvement predicted higher student engagement. The number before the slash is positive emotions, and after the slash for negative emotions. And then we find that the higher student engagement predicted higher positive emotions and lower negative emotions in teachers. And then we turn this into a random effect model. So we then find that there are individual differences between students in how they react to teachers' involvement. And then we find that there are differences in teachers in how students react to teacher involvement. And then to plot what this means, we plotted this graph where we have positive emotions to the left and negative emotions to the right. And here we can see that there's a differential effect that teachers, it depends on who teachers get involved with, and this has an effect on their teachers. So some students matter more for the teacher's emotions than others. So the steeper line, these students matter more. So when students the teacher was more involved with were more engaged, this predicted teacher's emotions more strongly. And the other way around, when students the teacher was more involved with were more engaged, this predicted teacher's emotions more strongly. And here, these are negative emotions, so it's a steeper downward trend for that pattern. So it matters whom the teacher, the reasons for the teacher's emotions differ according to which students they are then having dealt with. That makes sense?
Mm.
Yeah, okay. And then we go on and we look at whether teachers and students' emotions are reciprocally transmitted in the classroom. So if a teacher is happy, does that rub off on the students? And if the students are happy, does that rub off on the teacher? So which way does this work? What is hen and what is egg? This is the way we can solve this conundrum. So we have teachers report emotions, they're self-reported as student perceived, and teachers' emotions at time t. So concurrent time point and previous time point, and then we have student emotions at both time points.
And the student emotions are just self-report.
They're self-report, yeah. So teachers report themselves and students report themselves, but we didn't collect teacher reports of what the teacher thought the students felt. But that was over the top. But we got student reports of what they thought the teacher was up to. And we see that student emotions, here we have positive emotions. We see that the autoregressive coefficients are hover between 0.14 and 0.27. So there is some stability, but it's quite close to zero. So there's also quite a lot of fluctuations, and people return to their baselines quite quickly in emotions. So it suggests that emotions are quite short-lived in the classroom. They come and go and we'll see other autoregressive coefficients later that are stronger that we'll compare with. So emotions come and go quite a lot, but some stability there. And the interesting thing is then to see who affects whom. So we have teachers and students' positive emotions. These are self-reported by both the classroom. We see that teachers' positive emotions can rub off on students' positive emotions for the next lesson, but not the other way around. So students' positive emotions do not rub off on the teacher. We see that they're quite uncorrelated with each other in the classroom, which is quite interesting. So it also suggests that students and teachers live in quite different worlds and in their perceptions. Then we have student perceptions of teachers' positive emotions, and these were transmitted to students' positive emotions. So look at the key parameter there. So student perceived teacher positive emotions were then positively predicting students' positive emotions. And for negative emotions, we found quite interesting patterns. So we found both directions here. So it suggests that when students perceive that their teacher expressed negative emotions, this also made students more grumpy the following lesson. And when students were grumpy themselves, this also predicted their perception of the teacher. But this is in the eyes of the students, and this was not the case when we looked at teacher reports and student reports. So again, emotions do have quite a large perceptual component.
But the synchronous relations are much stronger.
These are much stronger, yeah, because this is probably the self-report bias, if we like. So this is the same reporter here. Students report on the teacher and students report on themselves. So they are more strongly correlated than in the previous graph, where we saw that when we have student and teacher reports, they are not correlated with each other. Yeah, they're quite separate.
Right, so maybe the teacher must be happy.
Yeah. So the next steps are to link teachers and student reports of student engagement. The research question being, do teacher and students agree with each other? So if students report that they are engaged, does the teacher also report that the students are engaged? And could a stronger agreement be explained by student-teacher relationship? This is a theorized relationship that is part of Beijing Li's doctoral dissertation. And now comes the time to test this really empirically as well. If students and teachers know each other well, then we hypothesize there should be a stronger agreement between when a teacher thinks a student is engaged and the student thinks that he or she is engaged. This is to come, so stay tuned for this. Models are going on, but not there yet. How am I doing on time?
Yeah, good.
Okay.
10 minutes.
So let's turn to Norway. This is following streets study and the proposed next steps of it. This was a shorter time series, so this is looking at mathematics lessons that took 4 mathematics lessons the first lesson was always introduction of a topic. It could, of course, be a reintroduction if they had done it previously. These are students in grade 6 and grade 10. So mathematics is a cyclical topic. So you build previous new topics, build on previous topics. But this is the first lesson. It's always a reintroduction of a topic for the students, and follow them up to the end of this topic. So we have both self-reports and observations, and we use the one tool called the ISTOF and one called the class observation tool. If we look at the individual differences in predicted self-efficacy, so we ask students, how confident are you? You can do the easy, medium, or hard tasks this lesson. See that there's quite a lot of variation in this pattern of their self-efficacy. So feeling confident at the beginning of the lesson. Then we ask at the end of the lesson, their mastery experience. That means to what extent were they successful in carrying out the easy, medium, and hard tasks. And these are the predicted values. And we see that lines go in all kinds of directions. So there's again a lot of variability here in those changes over time. So we specified a model to put all the self-efficacies together. It looked like this. I won't dwell on all the details. But long story short, we see that on average, students thought that they were quite efficacious for easy tasks, and for medium tasks, kind of upward trend. And for hard tasks, there was an even stronger upward task. So suggesting that the harder the task is, the more room there is for feeling successful in learning this task. There were also differences between the year groups, so that year 6 students thought that this self-efficacy beliefs were more malleable than the year 10 students. If we compare these two lines, so this is the self-efficacy for the year 6 students for hard tasks, and this is for year 10 students. So year 10 students have a more fixed perception of their self-efficacy from one lesson to the other. Very proudly received 1.3 million pounds from the Norwegian Research Council to carry out an empirical study. The data has now been collected, so instead of having one topic, she collected data up on 4 different mathematics topics, so spread quite evenly throughout the school year. And then we included something that was missing from the previous study, and this is a math task, a learning task that was administered at the end of each sequence to get a grip of, well, how well did the students then learn the contents that they were working on in this topic. So enhancing the previous design to this, and the other.
Nice test,
Yeah,
very
yeah.
specific to that.
Yeah, so very topic specific mathematics, not a generalized one. And the other expansion of the field is that we want to, coding has already started, to have instead of a classroom observation measure that captures the teacher's interaction with the whole class, we have started to code the teacher's interaction with each individual child for each lesson. This is very sparse data, because when you start coding at the individual student-teacher dyad level, there are many students who don't receive this attention from the teacher in each lesson. So this will be an important way to see whether an individualized instructional support or individualized emotional support can make a difference in the prediction of mastery experiences. And now
You report, or do you have videos?
they're coded from videos, yes. Yeah. So they go back and code one student.
Next generation stuff.
Yeah.
Stuff.
Yeah, and well, we're not as advanced as Rebecca Lars-Eriks talk yesterday. You came to the quantum where they trained AI to code the videos. So we're still doing it with human person power. So it will take a bit longer to code that data.
Lars,
Yeah.
but does that assume that if you ask Kathy's question, I don't learn.
No, I don't think it makes an assumption about don't learn, but
Yeah, I mean, if you're just coding
mm,
interaction with Kathy, and I haven't said anything, which of course I always do. If wouldn't I have had any interaction?
yeah, but I don't think the assumption is that the absence of interaction is problematic. I think it's really trying to capture where the interaction is happening. Because till now the class was just so global, right?
Yeah, no, I do
Yeah.
understand. I
Mhm.
do understand what you're trying to do, but
Yeah.
I'm sort of picking at the assumptions behind it,
Yeah,
you know.
well, we're thinking of it as a way of capturing individualized support in this dyad observation. And are there students who are in need of more individualized support? And if they get it, can they then perform better in mathematics? Can that boost their mastery experience? Your question was perhaps, well, if you code what me and Kathy are talking about and you sit next to Kathy, you will overhear what I tell Kathy and you will also benefit from that. So this is a side effect that I don't think we can control for.
But you can capture implicit learning
Mm.
because what you're doing is by using the interaction, you're capturing explicit teaching.
Mm.
But if she's also learning, you're capturing implicit learning
Mm.
because you've not done explicit teaching to her,
Mm.
but she's picked it up.
But you don't know how she did it.
Yeah, we don't know, but implicit learning mechanisms
yeah,
are
yeah.
clear. Yeah.
Yeah, but what I'm really talking about is when you look at the math task and try to predict it from these particular interactions,
Mm.
you know, hopefully everybody else is benefiting.
Yeah.
Otherwise, I would be very selfish right now.
Yeah, but the question is, are there some students who benefit differentially more than another student? And this is the whole idea of individualized or personalized learning, that teachers can tailor the support to the student's need. And this would be one way to find out whether that takes place or not. But this is the underlying idea, really. So stay tuned for findings there. We'll start the modeling very soon. Finally, let's take a look at links with objective measures. So we have various cognitive tasks, but I'll show you the study where we collected repeated measures of children's executive functions and their self-reported emotions. So 2 papers are out from that study. So this is the physical activity, engagement, and cognition study. We started up 2 weeks before COVID hit the schools in 2020. So we got a sample, quite a small sample, rather than the anticipated one of around 150. So we also spent quite a lot of methodological learning. So how do you model when you have quite a small sample at the between level? And there are ways to get that as well. So the design of the study was that we have a morning, noon, and afternoon self-report questionnaires or emotions that we will look at in a minute. And then we have the executive functioning task. It's called the hearts and flower task. And this was then administered once in the morning and once in the afternoon. In reality, students actually did the task, the executive functioning task, either in the morning or noon, but always in the afternoon. So the morning session is actually going to be sometime before noon, and the afternoon is then after that kind of midday break. We also strapped accelerometers on the children to look at the effect of physical activity, but those were only null findings. I think it's due to the sample size, so I won't discuss that right now. This is the heart and flower task. So when the heart appears on the screen of tablets, so we administer tablets to them that children worked on. And when the heart appears, you press the same side as the heart. And when the flower appears, you press the opposite side of the heart. And the mixed task that we then administered is a mixture of both congruent and incongruent tasks, and 60 of those in a row. And then we can look at individual differences again in the trajectories over time. So we have the response times in green that fluctuate from one situation to the next, and then we have the correctness of the tasks in black underneath. So the scaling goes from 0.55 to 1, and the response times are as short as half a second, 0.6 seconds or so, up to about 1.5 seconds. We see very different patterns of change over time, and children differ in these patterns. Here are all the participants, and we also see that these are also very different patterns over time. And we see that the accuracy and response time by time and since the start of the study. So if we then look at the test of the stationarity assumption, which means that there will be no mean level change over time, we see that children became less accurate over time. So they didn't become more accurate, they became less accurate, but they became faster over time. So it could be that when they speed up, they make more mistakes. Then we run the models. Not going into all detail, we'll look at the key coefficients here. First, we look at time effects, and we see that the time of day. So children were less accurate in the afternoons. They were less. The response time was faster later in the week. So it could be a training effect. They got faster from one time point to the next. And then the study day, these are the 10 days of the study. So they also got faster from the beginning to the end of the study. The next coefficient is the accuracy and response time. They were fairly stable across time. And if you remember the autoregressive coefficients for the emotions, these were between 0.14 and 0.20 something. We see that the stability of accuracy is larger, and the stability of response time is also stronger than that of the, so emotions come and go faster than the response time and accuracy. And then we included an accuracy or response time slope. And this is a credible effect with a large variance. To explicate what this effect means, that we looked at how does response time predict accuracy over time. And if we then see that the larger accuracy and response time slopes were associated with lower accuracy intercept. What does this mean? Let's draw a picture of that instead. So here each line represents one child, and we have a response time on the x-axis, and we have accuracy on the y-axis, and we see that those are different slopes. In the upper end, we have flatter slopes, and then we have steeper slopes. So larger accuracy and response time slopes were associated with lower accuracy intercepts or means. So children with higher means have flatter trajectories. So those who are on average doing well, they fluctuated less. And those who are on average were less accurate. When these children slowed down, they were more accurate. So when children with lower trait accuracy slow down, they are more accurate. So this is also, if you think of response time and accuracy for not only tasks like this, but for any task at school, asking children to, oh, you're going a little bit fast, slow down a little bit here, think before you go. These could be important prompts also for many children to have to slow down. Well, you're good at this, well, you could do it faster, so speed up a little bit. And this is what, if you have this response time accuracy balance in classrooms, this could actually be applied to any task that children do. This is the critique we also got from the reviewers, said, well, this is not a real world school task, because children in school, they don't repeat the executive functioning task 20 times over a week, but they do different tasks at different time points. This was still a way to get an objective measure of their cognition from one lesson to the next, and that was the importance of this objective measure. We then go to the last study. This is by Henry Lowe, my doctoral student, who some of you have met. He then refers to the different theories which say that if cognition can be overloaded, if there's too much negative emotion. So if anxiety is high, cognition can suffer from that. So we included emotions, self-reports, and then linked these with the executive functioning performance. So this is the accuracy that Henry is predicting here. And we can see that when children were more positive than their own average, their executive functioning was better. So happy children are more focused and do a better job. And when children were more negative than their own average, executive functioning was worse than their own average. So this is the comparison point in this model, to compare children against their own baseline. So when they deviate from their baseline on one variable, what is the effect on the other? So this was a nice finding. Importantly, we also asked children about their cognitive engagement and task difficulty and competence beliefs and effort, but these did not predict executive functioning performance. We haven't published that because null findings are not that popular in the literature, but I think we still should. To sum up, an intraindividual approach can get us rich process data for students, teachers, and student-teacher interactions. All students and teachers have their ups and downs, so their good and bad moments. How can teachers capitalize on teachable moments of all the students? So this is the individualized, personalized learning question, really. How can teachers capitalize on the good moments or then turn bad moments into good ones? Challenges with this type of data collection that is real world is it's time consuming and it's quite complex to accomplish. And you need quite advanced modeling, but that's an easy thing to learn if you want to head this direction. A possible future design, this is something in the planning with some Finnish colleagues. There is a national portal for mathematics and language tasks, so mother tongue tasks in Finland, where I'm from. There is one portal called Ville, which has these learning tasks, and many classrooms use Ville, for example, one lesson a week for maths. And design for this portal could be, and this is negotiations in progress. If we get student self-reports of working in classroom, so a mini questionnaire, and then they go and work in the portal. The portal administers a mini questionnaire. What was it like? How many did you? And then we get objective data from the portal and can compare what children do in math class in lessons and what they do in the portal. So this is a way, it's not naturally occurring, but this is taking advantage of the technology that is out there. And this would be very easy to implement in this Ville portal. And this would work well for kind of quite centralized systems. The Netherlands also has some 3-4 different portals that the primary schools use in different school subjects. And they also collect this type of data at the almost population level now. This is really a valuable resource for research that could be integrated into an intra-individual design. On the statistical side, there's a long debate on how large samples need to be for a study like this, or to put it as the good old university student question, how few can we get away with? Question. We see that some recommendations by Schultzberg and Musset suggest that we have 150 participants or more. Hence, you see a lot of intra-individual studies who aim at 150, including ourselves. If you read the paper really carefully, models really differ in how many participants they need, depending on how complex parameters you want to estimate in the model. And what we have learned from McNeish, my current statistical hero, is that you can have 10 to 50 participants and run models like this with so-called informative priors in a Bayesian modeling framework. And this will enable you to get really robust parameter estimates, also for when you have very few participants. And it's really the between level parameters, the student level that can go bonkers when you have too small samples there. but this can really stabilize the models. Another debate is about whether or not to use a Bayesian estimator. This has been implemented in a software called M+. And if you just treat it as an estimator to get results, or if you then want to embrace the whole philosophy of priors. Priors are educated guesses of what you think the result will be. And then the certainty of your guess is also indicated in the model. So the more certain you are about this is going to be a 0.25 because previous research says so, then you include this as a prior in your model, and the certainty is then captured in a variance parameter, variance of that parameter, and this will help stabilize modeling. There's quite a lot of debate about how you set these priors, and the critics are saying, well, that's very subjective how you choose priors. And the McNeish take is that you can use the descriptive data of a study for preparing priors for some parameters. And this has worked really well also in our study on the executive function with 46 participants. That's something I really like. So where's the big world out there heading? I mentioned nudge designs. So there is a good example by Breitwies and colleagues in Germany. These are university students who prepare for their medical doctors and preparing for an exam, written exam in medicine. And it's a 2-month sequence of visiting a learning portal where they have previous medicine tasks to carry out. And they set goals every morning, and then they have so-called nudges. How are you doing now? How did you fulfill the goals that you set up earlier? And a lot of prompts like this of, have you reached the goals of how long you wanted to study today, and so on and so forth. And then they look at their emotions and self-efficacy for studying medicine as well. So this is coming with nudge designs. I mentioned the integration with artificial intelligence and machine learning for analyzing data like this. This is something I haven't tried myself to let the machine touch my data, but others do. And the big world is also looking at something called network analysis, which I also haven't dwelled that much into. Method innovations include how to model nighttime and downtime. Some suggest that there's a different process during daytime from one lesson to another, and then the process that happens overnight is another. So you need to model these as different parameters in the model. So these are coming up. Do we use time covariance or residual DSEM models? And then we have models of volatility and innovation constructs and their interpretation. So this is a model that I've tried. I'm still working out how you really interpret this model. So we see that we have the residual here at the within level. And we see that this is specified as a random effect, which means that there are individual differences in how large the residual is. The residual is the unexplained variance of that variable. So we can explain then if there are individual differences in the residual or the unpredicted part of the model. And the people who come up with this idea suggest that these are all the things that happen to a person during the day. One's medication, if one is tired, if one has slept well, one's state of mind, anything that can affect a person's response on the outcome variable, but is not included in the study. So this essence picks up everything that wasn't measured and the effect of that. So it's a very interesting concept, and it's termed volatility in the literature. And I'm yet to see any really good substantive interpretations of this, but I'm sure they will be out quite soon. So they say stress sensitivity to the outside world is one interpretation of the volatility concept. Yeah, and it was pretty well planned. So here are all collaborators over the years, and thanks to our funders over the years. And if anyone is interested, I'm happy to tell you more about this. Yeah, thank you for the presentation. And this is from